think it's Constantinos preparing there. Yes, seems to be. Perfect. So Constantinos will talk about, of course, an IT conference without something about blockchains. So we get our blockchain talk now. And the following talk is about, say, combining game theory with, say, the tools of miners of blockchains. And I'm eager to learn how this can solve at least something in this world. Let's see.
Hello everyone, I'm Constantinos. I'm a postdoc in SWI, and first of all, thank you very much for this very nice event. And today I will talk to you about cool games about formation environments. This is a joint work with Dr. Marina Bitsaki from Computer Science Department, University of Crete. And let's start. Our motivation for this work is that the avalanche of digital environments, the big data era, the automated procedures that emerged in recent high-tech technologies, also that all needs a sophisticated digital transactions methodologies that are intelligible and crowdsourcing, and with parameter of, let's say, transparent transaction, like in e-commerce, Internet of Things, and several other areas that requires secure trading in distributed and decentralized environments. And one of these technologies emerged somewhere in 2008 with Bitcoin that provides the environment from the development of blockchain technology, where the blockchain technology is just a distributed, synchronized, secure database containing validated blocks of transactions. A block is just a container that holds a record of transactions on the blockchain. First of all, some terminology about the blockchain. A block is validated by special nodes called miners via the solution of a computational demanding problem like a cryptographic puzzle. This is called the proof of work puzzle, and the miners compete each other, and the first one that solves this demanding computational problem announces it. Then the block must be verified by a predefined agreement protocol called consensus, and after the protocol be verified, added to the blockchain. The miners that generate the blocks, meaning that solve the computational demanding problem, rewarded according to a predefined and a priori and commonly known protocol. But in several cases, the miners combine their forces together in order to increase the reward, and enter mining pools implemented by a pool manager. There, the pool manager, they provide partial proof of work concurrently, and with this, the pool manager can evaluate the miner's effort or to estimate the miner's power. If one of the miners manages to compute, to provide a full proof of work, then it shares the revenue along with the other members of the same pool. The utility of a pool is just the total sum of the revenues received by the miners, and the usual scenario is that of a block withholding attack, which means that the miner that solves the problem for some specific reasons does not submit it, after finding the block. This provides minimal cost for the miner, but from the pool perspective, this cost may be very large. Fortunately, this situation can be addressed using some classical tools from game theory, and specifically has been stated by AR in 2014 and D et al. In 2019. Specifically, in the case of AR, this situation is described as pool games. Now, in the pool games, the information available to each pool is the set of its miners, the set of adversary pools, and some predefined protocols that articulates the rewards and the procedure how the pool managers can estimate the power that they have in order to mine in the blockchain habitat. A pool may be attacked by a miner from an adversary pool by providing partial proof of work to the pool manager. The attacking miner then shares the reward provided by the loyal, let's say, members of the pool, but does not contribute anything. Thus, the utility of the attacked pool deteriorates and becomes less attractive to the other miners. The partial proof of work to opponent pools is called the infiltration rate. In our setting, first of all, we analyze and study the case where the pool game consists of n pools, where each pool, all pools have equal capabilities, and all miners are atomic and identical. Further, we examine this situation of pool games in three different information environments. The first one is the complete correct case, which produced in AR in 2014, and in a nutshell, it's the information where the pools know their mining power and estimate correctly the infiltration rates. The second one is the incomplete information case, where the pools are not aware about the size of the incoming attack. And finally, we have the incorrect information case, where the pools think they know the actual mining power of the pool and the accurate number of the incoming attacks. In our methodology, we have the number of pools denoted by the capital N, the number of choices that each pool has in its disposal denoted by the capital S, and the gains that each choice provides to the pools provided by this capital. In here, each pool tries to maximize its revenues, its gains, and from our perspective, our goal is actually to predict the behavior of the pools during this interaction, meaning to compute the outcome of this game. Using tools from classical game theory, this case can be articulated as a normal form game, and the outcome is none other than the Nash equilibrium point, where Nash equilibrium point is a joint decision where no agent, no pool, no player has incentives to deviate, which means that no pool can alter its decision and gain more. In the case of a complete formation, the normal form game can be articulated as Bayesian game, plugging into two more concepts. One is the types of the pools, where a type contains a private information that an individual information that the pool has about the interaction, and this type is observed by a specific pool about the channel information that has, and the utilities are calculated by each pool by taking expectations over the types according to their own conditional beliefs, meaning the conditional beliefs derived from the types. The outcome here is the bias variant of Nash equilibrium, and formally this stated by an extrinsic expected utility, where the extrinsic means that each pool knows its own types, but has no information about the types of the adversaries. The bias Nash equilibrium now is best responses against the choices of the opponents, taking condition to the types that this pool has for this interaction. In case of where the interaction is not one-shot, meaning that it's unraveled several time steps in a finite horizon, let's say, we have a repeated interaction, a repeated case, and the utilities can be computed either from undiscounted average of the utilities over the total time steps, or using a discounted case, a discounted formula, where the latter utilities are considered are more influence, have more influence rather than the first one. In the case of incorrect information, we utilize the concept of information gains, where an information gain is a table of normal gains. Each pool has its own subjective normal gain, and the actual the information of the actual interaction derives from this special normal gain denoted with G0. In our study, the misinformation affects only the values of the payoffs, and the outcome is the natural misformed equilibrium concept, which, in a nutshell, it's a joint decision where each pool derives its choices according to its view. And then these individual choices agglomerated and create this natural misformed equilibrium concept. In the repeat case, we utilize the adaptation procedure, which is a very simplistic update rule, meaning that after the construction of the natural misformed equilibrium, the environment provides to the pools, to the players, the actual rewards regarding this joint decision, and each pool individually alters, changes the rewards that it has in its own view. In the case where no information can be obtained to consecutive time steps, then the adaptation procedure terminates. And this is provided by the last formula, equation. In the pool case, as we have already stated, we have n pools, which in total have n miners in their disposal, and the goal is to maximize the revenue density. This can be obtained by optimizing filtration rates, and the revenue densities for a pool I is the average revenue that a miner can earn, compared to the average revenue you would have earned as a solo miner. The procedure is unraveled in discrete time steps, and a major assumption in our model is that the total number of miners per pool remains constant throughout the interaction. Furthermore, at time step T, a pool I has in total mi miners, commits to the pool J mij miners, and mines with power the total miners that it has minus the miners that commits to the adversaries. In case that this is divided with the mining rate, this is a direct mining concept, and shares the reward among the miners that commits to itself, plus the miners that committed to this pool by the adversaries in this interaction. Also having the infiltration matrix, which in each entry of this matrix it's a ratio between the miners that committed from I to J pool over the total number of miners committed to this pool. With this concept, we derive an iterative process, an iterative formula, where we can compute the revenue densities in each time step. In case of two pools, the infiltration rates are the miners committed by the pool 1 to pool 2, denoted by this M1 concept, and the miners that committed from 2 to 1, denoted by this M to 1. In this situation, each pool has two pure strategies, either to attack or not to attack the adversary, and thus in total we have 4 pure strategy profiles in this situation, in this interaction. considering the ordering of the revenue density revenues provided by AL, we have these preferences for each pool. It's not hard to see that in both cases, for both pools, the attack choice is more preferable. And if we restate the problem using the payoff matrix provided in the bottom of the slide, then you can see that the attack-attack joint decision is the most preferable. Also, this payoff matrix is none other than a version of prisoner's dilemma, and a benefit for this observation that the prisoner's dilemma has a unique Nash equilibrium, meaning that we expect to have only one outcome from this interaction, and also this is a pure Nash equilibrium, meaning that we have no these peculiar cases of mixed and randomized policies and choices. Schematically, the pool game can be depicted in this figure, where pool I commits M1 miners to mine for benefit, and commits also M1 miners to attack, to infiltrate pool 2 and deteriorate the efficiency of the second pool. In the case of complete information, we examine the simplistic scenario where the infiltration rates estimation has a level of uncertainty, and we only from the perspective of one pool. In a time step T, pool 2 estimates with probability V1 that the adversary attacks with the correct infiltration rates. Also with probability P2, estimates that pool 1 attacks with infiltration rates that differ from the correct case, meaning that now we have this M hat 1-2 infiltration rate function. On the other hand, pool 1 does not experience any uncertainty, thus it has the correct infiltration rates. Plugging this into the Bayesian game framework, we have this table of Bayesian game. Pool 1 has only one information type. Pool 2 has two information types, and with this at hand, we recast this incomplete information case in these two tables, table 1 and table 2, where we compute the outcome of this interaction. Some theoretical results in the case of the complete information is that we prove that this procedure, this case where we have convergence for the density revenues. In the first case, for all information types, if the infiltration rates are non-zero polynomials of equal degree with non-negative coefficients, such that the infiltration rates, the miners that a pool commits to itself are more than the miners commits to attack the other pools, then we have this convergence result. Also, we have a convergence result in case where the infiltration rate functions are bounded and this infiltration matrix has a norm less than 1 for all information types. Some numerical results that are in line with our theoretical findings. Both cases for the other one is the infiltration rates are linear functions. The lower one are cubic functions, and the initial infiltration rates follow are according to the table in the bottom left of this slide. You can see that the convergence is clear for this case. In the case of correct formation, again the setting is very simplistic. The actual situation depicted by table 3, this is the actual, the real interaction. The pool 1 observes, believes the table 4, the information as provided by table 4, and finally the pool 2 knows the pool game as provided by table 5. In this case, each pool 1 will take its decision according to table 4 and pool 2 according to table 5. In this case, the pool 1 will pick the S1 choice. Similarly, the pool 2 will choose the S1 policies. So the natural hemispheric equilibrium here is the S1. This is a pool game, okay? And after they reach the joint decision and construct the natural hemispheric equilibrium, then the environment will provide to these two pools the actual values for this joint decision, and then the agents, the pools, will correct, update the information they have about this joint decision, and now in this specific entry in the table 6 and 7, they have the correct values as provided by table 3. Because in this case we have the interactions among two players with two clear strategies for each player, then easily we can see that the adaptation procedure, meaning all this update procedure, will terminate in few steps, as it has only to traverse 4 entries in the payoff matrices. Also, some theoretical results. In the case of incorrect information, we prove that in some cases we can attain convergence in the density revenues. The assumptions are similar in the case of incomplete information, meaning that now, in case where the infiltration rates are non-zero polynomials of equal degree with non-negative coefficients, such that the infiltration rates of every pool in any view, in any subjective game, is more than the minus that commits to the adversaries, then we have this positive result. Also, in the case where the infiltration rate functions are bounded and the infiltration matrices have norm less than 1 for any subjective view in this form of the game, then also we have convergence for the density revenues, and some numerical results also that are in line with our theoretical findings. The setting is similar with the slide in the case of complete formation. The interesting observation here is if you can see in the bottom, in the upper figure, the dashed yellow graph curve has this sharp edge in the path when path is equal to 4, meaning that the adaptation procedure kicks in and the pools update their information, and that's why they have now different values, and that's why this edge, this angle appeared in this graph. Finally, some conclusions is that in this work we examine the blockchain interactions, specifically the pool games. We improve the theoretical results from et al. In the case of complete correct formation. Also, we transfuse the pool game setting to the incomplete and the incorrect formation cases, and further we provide theoretical results about this setting. Finally, some future directions for this work is to develop some mechanisms or protocols to regulate the efficiency of a pool game, and finally to study situation where other than the block with holding attack scenario. Thank you very much.
So, thank you, Constantinos. Remember the questions for tomorrow's poster session, and Frank, do you have any?
Absolutely, don't leave the room.
Absolutely. Yeah. Frank?
So, as every year, we have a winner of the